Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Mahesh Balakrishnan. He's from Cornell University, Ken Burman student, and he's going to talk about reliable communications in data centers.
Thanks, Jeetu. So, as Jeetu said, I'm Mahesh Balakrishnan. I'm from Cornell University. That's a very rare picture of Cornell. You can see it's not snowing. And today I'm going to be talking about reliable communication for data centers. So commodity data centers emerged in the mid-90s. Internet service companies found that they could scale to millions of users by using server farms of inexpensive machines. Now, the technical insight behind that is simple. First-generation internet services were extremely parallel. Economically, though, commodity data centers were revolutionary. They allowed companies to acquire and maintain massive infrastructure on shoestring budgets. Since then, practically everyone's jumped onto the data center bandwagon, and data centers have supplanted big iron computing as the de facto platform for any kind of scalable application. However, today's data centers are different from their predecessors in two ways. Firstly, data centers no longer act in isolation. They interact with other data centers that are geographically remote. Now, the links between these data centers are typically high-speed optical networks. Companies are deploying such networks because it gives them immense value. It allows them to mirror data to remote locations, to, for locality to clients, for disaster tolerance, for locality to outsourcing hubs. And this picture is increasingly looking like the network map of any modern corporation. Also, data centers are now real-time. Now, real-time is a loaded word, and it means different things to different people. In one sense, data centers are real-time because you're running applications traditionally considered real-time. Domains such as finance and aerospace, which are traditionally real-time, are moving to commodity platforms. However, in a completely different sense, we are going towards a world where people are storing all data and functionality within data centers. If I open my laptop and I store some data on it, I edit a blog, I send an email to someone, all that is being funneled through a remote data center. The data center is the computer. This is almost an extension of Sun's slogan from the 90s, the network is the computer. And the interesting corollary is that if when I open my machine, if all of what I do on it is being funneled into a remote data center, then I expect the same responsiveness from that remote data center that I do from my local machine. So data centers are real-time in that sense. They have to be extremely responsive. Now, Gartner did a survey of data center operators where it asked them, let's define a real-time infrastructure as a data center that recovers from failures in seconds or minutes. And they asked people, do you think this is important and do you have it? And those were the answers. Most people thought it was important. Most people did not have any kind of real-time recovery capability. And that leads us to the big challenge. How do we build a real-time data center, one that can recover from faults and other disruptive events within seconds? And this is a huge deal, right? This is almost a grand challenge. It involves dealing with literally dozens of failure modes at every level of the software stack. And it's kind of the backdrop for my PhD thesis. I looked at various failure modes within data centers and between them, and I built several systems that tackled different faults. Now, this talk is going to be about mechanisms at the network level. If you want to build a system that recovers within seconds from failures, you need to provide it with network primitives that recover in milliseconds from bad stuff that happens in the network. Specifically, we want to recover from packet loss in the network, and we want to recover extremely rapidly. Now, the insight here is that existing protocols are reactive. When something wrong happens, they react to it, and often there is a cost of reaction and a latency of reaction, and both can often be very high. Now, we are going to introduce proactive protocols where you inject the overheads a priori and you get immediate recovery when anything goes wrong. So in this talk, I'm going to be talking about two systems. One is called Maelstrom, and it's a protocol for reliable communication between data centers on these high-speed optical links that span thousands of miles. And second, I'm going to be talking about Ricochet, which is a reliable multicast protocol for within data centers. So moving on to Maelstrom, today the the only option you have for reliable communication between data centers is commodity TCP/IP. If you're running a commodity data center, you're going to be running Windows or Linux, and they have commodity stacks. So what happens when you open a connection between here and New York? Well, TCP has 3 problems. Problem number 1 is throughput collapse due to loss in the network. TCP was historically designed for shared congested internets, and it does not work well when used over long-haul high-speed networks. And it's egregious. If you lose 0.1% of your packets on a link, your throughput is less than 10 Mbps on essentially a 40 gig link. Now, this is a problem that's extremely well known in academia. It's been studied for 10 years. People have come up with all kinds of new protocols. I know that you guys are building compound TCP. The Linux community is adopting BIC. However, today the most commonly deployed protocol in the wild is still Reno, and that's a protocol that's over 10 years old. Problem number 2 with TCP is that it requires really large buffers at the end host for high rate traffic. Again, there are new variants that deal with this problem, but again, the end host may not have enough memory capacity to buffer that much data. So right now, the way that companies deal with it is they hire people to go around tuning TCP buffers. Problem number 3 is that TCP intrinsically has a feedback loop built into it. When you lose a packet, the receiver goes back to the sender to recover the lost packet. So it really does matter for TCP whether your data centers are next to each other or on different continents or on different planets. So what do people do about this? Well, solution number 1 is you just sit and you twiddle your thumbs and you wait for the operating system companies to deploy new, better versions. What do companies do today when they're still running on XP or some older variant of Windows or Linux? Well, they do multiple things, and they tend to generally be quite ad hoc. They rewrite applications, they try to use multiple flows instead of one, they go around tuning TCP buffers. But the most common solution to this list of problems is they throw money at it, or at least they try to. You could pay an ISP $1 million, and the ISP will give you the perfect network, a network that does not drop packets. And this is done today. ISPs give you a service level agreement which says the network will not lose more than X% of your traffic. If it does, we will compensate you financially. So that's the model today. You just throw money at it, you get a perfect network, you stop worrying about what's wrong with TCP. Now the question is, what if I don't have $1 million? What if I want intercontinental connectivity and I want it for $50,000 or whatever? Well, we have one data point for such a network, and it's called TeraGrid. TeraGrid is a network of supercomputers in the US. It has multiple high-profile sites, including NCSA in San Diego. And this is a fairly heavily used network. It's used on a day-to-day basis by e-science researchers. Now notice that firstly, the links between sites are 10 to 40 gigabits per second, and they're really not loaded on over a 3-month period, we never saw link utilization more than 70%. Secondly, the path between any two of these sites has multiple hops in it, and this is a fairly standard kind of topology that's being deployed out there for these kind of networks. Now, TeraGrid has loss even though it's not congested. It has a monitoring framework where sites pick other sites and they send a blast of UDP traffic and they note down the associated loss rate. And we saw something extremely surprising. We found that 24% of all these measurements had a loss rate of greater than 0.01%, enough to flatline any kind of TCP you're running on top of it. Now, we dug into this data and we tried to figure out what is going on, and we found that there were two reasons. Reason one for loss was that the pathway between two nodes in different data center was cluttered. There were multiple active devices. These active devices would just start dropping packets for no reason. We found faulty rate limiters, ingress routers that had bad NICs that were just dropping packets. And because these guys were not paying someone $1 million, to go and pull that card and replace it, you saw persistent loss. In an academic setting, nobody cares if you're losing UDP packets. They're just using blast protocols anyway. They're just making do with blasting packet across the pipe, so they didn't care. Now, talking to people more, we found that another source of loss on these networks was lossy fiber. Now, that's not true for TeraGrid, but apparently a lot of the fiber in the ground in the US has a certain spec. It's designed for, say, 1 Gbps or 10 Gbps. And when you try to run a laser that can multiplex 100 gigs on top of this, you see noise. Noise translates into a bit error rate translates into a packet loss rate. So we are in this world where you have infinite bandwidth essentially, but you have loss. You have very noisy, high bandwidth mediums. And we want to run unmodified TCP/IP on top of these networks. So how do we do this? Well, here is how. This shows the data path between two data centers, and you have loss occurring in the middle. By the way, so Jeetu told me people don't ask questions in the first 5 to 10 minutes, but now it's open house. You can, yeah. Go on.
I have a question.
Go on.
Okay, so part of your motivation, it seems, is that 10 megabits per second is not a good upper limit for a given TCP flow. Yet, it seems like in each data center there are lots of hosts that want to communicate or to hosts in other data centers. So in aggregate, it would seem that there are many, many flows, each one of which is capped at 10 megabits per second.
Sure.
If that's the case, then does one in aggregate saturate a 40 gigabit per second link?
I think between two data centers, you're going to see all kinds of traffic. You're going to have SSH sessions, which are very interactive. You're going to have file transfers, which is one big chunk of data. You could have 1,000 low rate. Essentially, I don't want to think about it. I do not want to reason about what kind of traffic there is. I want one solution that fixes every single problem that TCP has. And I'm going to show you that we can get to that.
Okay.
Yeah.
But in your experiments, how did you make sure the loss was due to these two reasons, not
we couldn't. Right now, we are deploying essentially. So there's a real network, and when we suggested that we should have access to the route inside it, people were not very happy. So a lot of the experiments are on test beds where we inject loss artificially. Right now, we are doing something interesting. We are using the Cornell site on that network to inject a routing loop so we can send traffic out and measure it. But that involves a lot of talking to network admins, and it's something we're doing now. Yeah.
Sort of my question. The sonnet layer will give you severe error in seconds. Just ask it. Did you look at that?
So these are essentially gigabit Ethernet, pretty much. In some sense, here in some sense is the problem motivation, right? You could fix all the problems I'm talking about by fiddling around in the electronics, in the network, changing the optics. We don't want to. I want the ability to just ask the ISP, give me bandwidth. I'm not, asking for an SLA. I don't want you to go around pulling router cards out and replacing them on the fly, but just give me the bandwidth.
The loss is just low loss.
It could be random, it could be bursty, it could be high, and we want a solution that fixes all of that, with the one assumption that bandwidth is not a limited resource. And maybe let me just describe the solution, and I think it becomes a little clearer. So I'm going to drop a box between the data center and the wide area link, and this box is a passive device. That's very important. If it fails, nothing goes wrong. You're still getting routing between the two data centers, and it's completely transparent. Your end hosts are still running TCP, Reno, whatever you want to. The network is not modified. It's whatever the ISP gave you. It could be dropping packets at varying rates with varying correlation patterns. And the way we do this is by using a very almost a time-honored technique. We're going to use forward error correction, right? Now, what is FEC? It's been around for decades. It's been used in link-level solutions for satellite communications, in fact, on CDs for encoding against errors. And FEC is this simple idea that you have a communication channel, and you have the sender inject redundancy into it that the receiver can use to recover lost data. In this example, this shows a Reed-Solomon code. It's one of the more common ones. And it shows that for every 5 data packets that the sender sends out, it generates 3 error correction packets, injects it into the link. Now, the receiver can recover from the loss of any 3 packets. Now, FEC is very nice because it has this property that recovery latency does not depend on the round trip time. So now it does not matter anymore if your data center is in Asia or anywhere. And the other nice property it has is that at any given point, you know exactly how much of your network is overhead. You can tune TCP to say, for every 5 data packets, generate 1 error correction packet, and that's exactly how much overhead you have in the network. No reactive storms, no network going down due to things like acknowledgements. Now, in the last 10 years, people have proposed packet level FEC. Incidentally, a person who's right now at Microsoft proposed that. And this is a nice idea because it's inexpensive. You can just run it on your machine. You don't need extra hardware. However, two things have stopped packet level FEC at end host from being deployed. One is that you can't go around changing end host stacks, and that in some sense you can get around. The bigger, more fundamental problem is that you don't get this RTT independence for free. You get it by trading off. Now recovery latency depends not on the RTT, but on the data rate in the channel. So now if you're running FEC end-to-end between two machines in two different data centers, and it's something like an SSH session where you're just sending a packet and you're waiting, well, you can't encode fast enough. And you can see why. I mean, in this example, the sender does not create any error correction traffic until he has enough data. So if the sender is sending a packet every second, then he has to wait for 5 seconds before generating any error correction packets, and the receiver has to wait that much time before recovering any lost packet. So how are we going to get around this? We can't do end-to-end FEC, even though it's a great idea, it's end-to-end, covers any possible kind of loss, but we can't do it because the data rates are not high enough machine to machine. So what are we going to do? We're going to push FEC into the network where we can actually aggregate traffic. And now this is a general idea, but the simplest instantiation of this is a box. You do FEC in a middle box. The middle box sits between your end host and the data center, your end host and the wide area link, and it does FEC for you. Now there is the simplest possible instantiation. Later in this talk, I'll show you exactly the same idea in a much more sophisticated implementation. Yeah.
To FEC, why can't we just inject some padding packets if we wait?
Because you have thousands of channels in your data center. It may be true that your machine is sending one packet, but the other guy could be sending a blitz of packets.
Yes,
Yeah.
I understand you can aggregate inside the network, but I'm saying if you the other choice for end-to-end FEC is if for a single host, if there's not enough traffic, you can just
pad
some
it.
pad
No, I understand that, but then you lose the property, which to me is very important, that your network link at any given point has X% traffic.
But that's the problem with FEC anyway, right?
No, if you aggregate in the box, you're now aggregating over a gigabit per second. You don't have to ever pad. You know exactly how much you're sending into the network. Now that for me is a very nice property because you can go to your ISP and you can say I want X bandwidth. You know exactly how much data, good put, you can send on the network now.
It's a trade-off.
No.
What is the, yeah.
I have a question which is just, I understand your qualitative answer to Wei Dong's question. Do you also later have a quantitative?
Yeah.
Okay.
We should. I mean, in some sense, I don't understand the objection. If I have enough rate, data rate, packets coming in, and I never do padding, then I know exactly how many error correction packets I'm generating per data packet. So I know exactly how much of my network is overhead due to the FEC. So,
But on the other hand,
Can I express it, Wei Dong's objection in a
Yeah.
different way?
Okay.
So I think that when you've got hosts sending, if you were to do a graph of hosts and how much traffic they're
Sure.
sending, we're looking at the tail where you're going to be generating these extra packets. So you're taking a small amount of traffic and doubling it, which shouldn't really matter much. And so when if you're justifying, there's two ways you can make this argument. One is that it will work on the net if you're aggregating them all together.
Sure.
But if you want to throw away the idea that it would work if the machines are doing it individually, you need to show that taking that thin tail and doubling it really hurts you.
okay, I get your point now. You have, I would say, if you have 100 nodes in each data center and they're interacting in arbitrary patterns, the number of channels you have could be extremely high. So you would have a very long tail, potentially. If I have 5 SSH sessions open to different machines in a different data center, and everyone in my office does, you get a problem where everyone's just waiting or padding. Maybe you don't buy that. We should probably take it offline. But that's my assumption, that you could have a lot of very low rate channels, and I don't want to do padding. Yeah.
Do you have data to support that inter-data center traffic
I do
does
not.
not have?
I do not. I would love to get my hands on that data, but it
Because presumably
belongs.
these servers are serving lots of requests. It's not,
Sure.
they have thousands
Sure.
of sessions.
I'll just say, we don't have that data, and so we're just trying to solve any possible pattern of traffic. I'll just go on. So how exactly does this work? Well, on top you have the send side data center, on the bottom you have the receive side data center. The send side appliance is snooping traffic that's leaving the data center. It's creating what for now you can think of as XORs. So every 5 data packets it's creating an XOR, dumping it into the channel. The receive side appliance picks up these XORs and it uses them to recover lost packets. Now note that the receive side client, which should be on the other end of that arrow on the bottom, does not see any loss. It will see out of order arrival, and hence we need to recover packets extremely fast. It's very important that we recover packets immediately, otherwise TCP IP will perceive out of order arrival. So I said we are using XORs. We're using something a little more sophisticated. So what happens if you have bursty and correlated loss? Well, forward error correction has always had this other problem. The elephant in the room in some sense is that it's not very good at handling bursty loss patterns. If you lose 10 packets in a row, all bets are off. Now, for traditional FEC encodings, the recovery latency that you get from a code depends on the maximum burst size it can tolerate. The way they do this is they interleave coding, so they split one big stream into a lot of little streams, they encode separately over these streams, and hence they get a proportional increase in burst tolerance. But this also means that you have to wait longer and longer for recovery to happen, because now you are encoding over low rate channels. And remember I said recovery latency depends on the data rate in the channel. So we came up with a new code that has a graceful degradation curve. The goal is if I lose a single packet, I want to recover it immediately. If I lose 10 in a row, I want to recover it in 10 milliseconds. If I lose 100 in a row, I want it to be recovered in 100 milliseconds. And the way we do this is fairly simple. We just create XORs at different interleaves. So we create one layer of XORs out of consecutive packets, another layer from every 10th, a third layer from every 100th, and so on. Now this means that for constant overhead, given a FEC code, we get this graceful degradation curve in latency that no other FEC code has. We don't get it for free. We have to trade off on the recovery power of the code. So this compares the Maelstrom code to Reed-Solomon, which is the canonical FEC code. And you can see that we lose a little bit in recovery power, but not that much. And in return, we get much better latency properties. Yeah.
Is this the most optimal thing to do?
So I spend a lot of time convincing people it is. And if they're not convinced, my answer is, look, if you have a better code, I've given you a way to deploy it. So that usually either they agree with me. If they don't, I just tell them, okay, you think you have a better code, you can deploy it.
I'm just questioning whether Reed-Solomon is the optimal thing to do it.
Oh, Reed-Solomon. It has constant overhead. So that's the key for me. That if you use a lot of the newer codes, do not give you this property that you get exactly this overhead. For example, rateless codes, which is what Michael Walsh has mentioned at NSDI, the argument there is, and this is also true for something more recently called growth codes, the argument there is you change the overhead to get burst tolerance, and we don't want to do that because this is at the network level. Well, that may not be, I mean, I want the guarantee that 75% of all my bandwidth is pure overhead, and I don't want to go around tweaking that. That's one set of things to optimize against. If you don't...
Why do you want to do that? I mean, isn't it sufficient to say that you will not exceed the network capacity?
I think, Jito, the history here is that a lot of protocols that failed in some sense failed because they were reactive, as in they do something, something happens on the network and they react to it. And this is true for things like multicast protocols where there are broadcast storms and you have NAC storms and stuff like that. So we are trying to come up with a protocol that essentially is the most passive thing on earth. It does not react, it just injects this much overhead. And hence you can very predictably plan around it. Now that may not be a goal that you think is important, but that's kind of the assumption behind this. So Maelstrom operates at the IP level. It can do two things with TCP. It can ignore it, in which case it's just working at the IP level. TCP end-to-end flow control is maintained, and it's a passive device. If it fails, nothing goes wrong, and that's the version on top. However, that solves only 2 of the 3 problems with TCP. It eliminates loss. It does not handle the buffering problem. So to solve that problem, we can also use the Maelstrom appliance in the critical path where we make it an active device. It intercepts and breaks TCP flow control. And that's nice for some applications that want to handle buffering outside the end host. but it does convert it into an active device. So we implemented this, and we were able to build a prototype that runs on a commodity box, and it runs at a gigabit per second. It's limited by the NIC, the outbound NIC. And if we had a 10 gig NIC, we'd probably be able to run it around 3 Gbps. And how does this work? So here is a graph that shows what happens to TCP when loss occurs in the network. On top you have TCP without loss, and we're stretching the link out. And on the bottom you have TCP with loss. So you can see throughput just collapses completely when you have a loss rate. Now we introduce Maelstrom in the middle, and we get 3 lines that are indistinguishable at different loss rates, and they're very close to the TCP lossless curve. So yeah.
How many flows do you have in this?
We were running, I think we were running somewhere between 10 and 20 flows in parallel. So we did expect that as you increase the number of flows, you won't see the collapse. But
Yeah, the more flows
Yeah.
you have, the
but
less-
apparently the effective observed loss rate by a flow is still high enough to completely flatline it. And we found these results were with Reno, but we ran it on BIC as well. And very surprisingly, we got almost the same curve. We're trying to figure out exactly why that is. Maybe it's just a artifact of the loss model. But
The other day I heard a practice talk about TCP Illinois, and they claim
Uh-huh.
they do it much better than other.
so
traditional-
most of the new protocols either use a different control curve or they use delay. And I think compound TCP does both. In either case, I don't want to comment on the newer work because I know I have not run against every protocol out there, and it's possible that for this loss model some of them would behave much better. But the strongest claim I can make is that look, for the most commonly deployed protocols out there, this does happen. But yeah, sure, you can fix it if you play around with TCP. I do believe that. Okay, so you can see that at 25 milliseconds we don't track TCP, and that's because we're limited by the outbound NIC. We have around 650 Mbps of good put, and yeah.
Sorry, is this a simulation or a measurement on a
This is an actual evaluation on a test bed, though it's not the actual TeraGrid system.
How is loss being injected?
Loss is being injected, let's see. We're doing it artificially at the network level. It turns out to not be very complicated. We just drop packets. Yeah.
Are they just uncorrelated random losses, or are there bursts?
These are random. I have slides for Bursty later. Yeah.
A couple slides ago you mentioned this split mode. That means you need to change the end host.
No. So this is a fairly standard thing. People have built performance enhancing proxies, and the idea is that if I try to send a packet from here, there's a box that intercepts that, breaks the connection, and then does the buffering for me. So the other interesting thing in this graph is as you pull the link out, your throughput is going down even when no loss occurs. Yeah.
You were talking about the gap between the 650 and
Yeah.
the 900, and the cause that gap is.
So the box can handle a gigabit per second of traffic going out. We are adding FEC, so FEC plus data is around a gigabit per second. We are adding maybe 25% overhead in these experiments. If we had a bigger NIC, we'd be running at a gig. But obviously, the moment you hit the bandwidth ceiling, you're going to have this problem that good put is lower. So throughput is going down with the length of the link, and that's the problem with buffering that I talked about. That as you stretch the link out, you need bigger buffers at the end host. If you don't change the buffers, this is the phenomenon you observe. So if we change Maelstrom into an active device, now it's on the critical path, it can fail, things can go wrong, but we essentially get this property that throughput is independent of the RTT. The third claim is that Maelstrom handles the recovery delay problems with TCP. So on the left we have, you can see that when you have a loss rate, TCP/IP has these massive delivery spikes. And one reason for the spike is that the receiver buffers all incoming data because TCP supports sequence delivery, and hence if I lose a packet at the receiver, I have to wait, I have to buffer all incoming packets until the missing one is recovered. That's one source of delays. The other source is that congestion control kicks in and now the sender is buffering as well. And on the right you can see that by adding FEC we eliminate all loss. That's kind of a trivial observation. More interestingly, you can see that for normal data packets we are not adding any latency, they're just getting routed. For data packets we are recovering it extremely fast. There is absolutely no difference between recovered packets, maybe a few milliseconds. So how does the code work? The layered interleaving code I talked about. So we have these histograms of packet recovery latencies. On the left, we show that if you have completely random losses, most packets are being recovered almost immediately. You just have one big bar at the beginning. As we make losses burstier and burstier to the point where you're losing 20 packets in a row or 40 packets in a row, you can see the histogram is shifting to the right. So we're getting this property that the recovery latency depends on the burst length. So before I go on to the next part of this talk, I'll give you an opportunity to ask questions, but I just want to mention other work we're doing on top of this. The reason we started looking at this problem of inter-data center communication was because we were approached by financial institutions that needed mirroring solutions for disaster tolerance. And the state of the art right now is that banks in New York place their mirrors in New Jersey for disaster tolerance. And that's as far as they can go. And what they ideally want to do is place it somewhere in Kentucky. And the reason for that is there are really only two ways you can do mirroring right now. You can, when I write to the file system can send the data to a mirror and wait for an acknowledgement, and that's extremely safe, but it's extremely slow. The other option is you just return to the application and you just assume that the packet gets there. Now, we're exploring a middle ground. What if we add so much overhead into the network, so much redundancy, that we can push the reliability level of a piece of data to the point where it's as safe as if we wrote it to a local disk. So we built a file system that does this. It essentially returns to the user once the probability of losing the data is high enough, assuming that data is lost in the network. So I'm going to move on to Ricochet now, which is the other protocol, but do you have any questions at this point? Yeah.
Is there really much purpose in handling large burst losses? Because of those length of time to recover, TCP is going to notice.
Absolutely, you're right. To a certain percent, we can make it transparent to TCP. Beyond that, we can't. But I'd argue that there are, one of the nice things about this work is it works at the IP level. You can use any protocol on top of it. It transparently increases performance. So arguably, it still has value. Yeah.
It seems like you can't completely hide the semantics difference between waiting for an app and not. I mean, if I unplug the network, then no amount of FPC is going to save it.
Yeah. So it's a very narrow model. You're right. It works only if the reason the packet gets across is loss in the network, not a disconnect or something. You're right.
Or a failure, for instance, if you're active.
Sure.
Right.
It's a very narrow model. I do agree with that. But we think that it provides value to people who don't need complete safety but don't want to go the other way as well. So that was Maelstrom. It's for reliability between data centers. Now I'm going to show you that the same kind of techniques using forward error correction in interesting ways can have a lot of value within data centers as well. So what's the connection? Well, in the inter data center case, one of the main reasons we wanted to use TCP was because you can't have a feedback loop from the receiver going back to the sender. The length of the link is simply too high. And hence we wanted this property that all communication is just one way. Now within a data center, the RTTs are not very high, but the standard mode of communication is multicast. And if you have a lot of receivers for multicast, you again have the same problem where the receivers are not very far away, but there are just too many of them. So if you wrote an acknowledgement based protocol which has a very tight feedback loop, then for every packet the sender sends out, he's going to get swamped by incoming acknowledgements. So you can't have a feedback loop in either case. And we're going to use the same kind of techniques in this setting now. But before I talk about that, is multicast used in data centers? Why is it used and how is it used? So within data centers, data is often sprayed across multiple nodes. It's partitioned, it's replicated. People use a whole number of communication paradigms to do this. They use pub-sub products. You can imagine caching and validation groups. And the example I'm going to give you is from a financial setting where you have nodes that are subscribed to portfolios of equities. So you have a node that's tracking a number of stocks, and the way that it's done today is each equity is mapped to a group, a multicast group. So if I'm interested in an equity, I join the multicast group and I get the update for that group. Now this means that each node is, and if it's interested in hundreds of equities, it's going to belong to many different groups, which means that the granularity of a single group is going to be fine, which means that the data rate in a single group could be fairly low. you're not going to get 1,000 updates for the Microsoft stock, you're going to get one every other second or something like that. However, even though a node is in a lot of low data rate groups, it can easily get overloaded. It's tracking 100 equities, maybe 1,000, and if there's any kind of traffic spike, the node gets overloaded. Now, multicast protocols are UDP based, and hence nodes can get overloaded. They can drop packets at the buffers. And when we looked at this 2 to 3 years back, the dominant model was for nodes to be very thin. You have thin blades running on a very fast network. They can get easily overwhelmed. Yeah.
So you are talking about application level
Multicast part. You say it's a
We are running on top of IP multicast, but the reliability layer, at least with current technology, is always application level. You're right. So what happens when nodes get overloaded? They drop packets, and we found that it was ridiculously easy to overload a blade server. On top, you have a blade server that's getting more data than it can handle. On bottom, you have one that's getting less data than it can handle. They're in the same groups, but the one on top has an extra group, and they're behind the same switching segment. So what this graph is saying is that A, loss is occurring at the end host. It's independent across nodes. It's not in the network, and it's bursty. So it's happening because of kernel buffer overflows. So how do we deal with this problem? Reliable multicast is a very well-studied problem. It's been around for years, and it's been solved. Scalable multicast is a solved problem. However, when people say scalability, they mean scalability in the number of receivers. There's been all this work that looks at how to scale multicast to hundreds, thousands, millions of receivers. In a data center, though, you want multicast where you can have lots of receivers, sure, but also lots of senders to a group. What if a node is aggregating data from many different senders? And that's something that nobody has looked at before. And also, you want to support a lot of overlapping groups. Each node is in hundreds of groups. So I want to support a system where multicast is used at very fine granularity, where you can use it at the item level or the object level. So how do we do this today? Well, there are only a certain number of protocols you can write to solve this problem. Number one is you just use acknowledgements. You just translate TCP style reliability to multicast. This does not work because you get ACK implosion. I already mentioned that. Number two is you use negative acknowledgements, and this is how all commercial multicast technology is built. There's a protocol called SRM in 95 or 96 by Sally Floyd, and that's been translated by companies including Microsoft into better protocols that essentially use negative acknowledgements. Now I'll come back to what the problem is with this in a minute. Number three is you can just inject FEC at the sender. So the sender creates XORs, injects them into the channel, and nodes recover from loss. Now the problem here is that if you have hundreds to thousands of low rate groups, you get the same issue, that you can't use padding, and FEC doesn't work very well. The latency depends on the data rate in the channel. Now this artifact applies to negative acknowledgement protocols as well. The receiver does not know it's dropped a packet until it receives the next packet from the same sender to the same group. In a setting where you have hundreds of senders and hundreds of groups, this could be seconds. So what do? We're going to apply the same technique we did in the last set of work. We're going to move FEC into a location where we can aggregate over high rate data channels. We're going to have receivers generate XORs, and we're going to have receivers pass around these XORs that can then be used to recover lost data. Remember, I showed you that loss is occurring at the end host. It's independent across end hosts, and hence this actually works. The receiver on top misses data, it gets an XOR with that data, and it can recover the missing packet. How exactly does this work? So each receiver is generating XORs over incoming data packets, and it creates an XOR and it picks C other nodes in the system, and it sends the XOR to them. Now this gives you essentially a forward error correction rate. You know that your system is X% overhead. And it has the interesting property that you just removed the sender from the reliability protocol, and hence now you don't care if you have one sender or you have 1,000 senders. You are completely oblivious to the number of senders to the group. It's a completely receiver driven protocol. So we got property number two. We already have scalability in the number of receivers. That's the easy one. Now we have scalability in the number of senders to the group. What about the next step? Can we get scalability in the number of groups in the system? Well, here's how we do it. So this shows how the protocol I described in the last slide works. You have two receivers. They're in two different groups. They're sending each other XORs. So receiver R1 sends R2 two XORs, one from data in group A, another from data in group B, and it does these independently. It's running two versions of the last protocol. But we can do better, right? We can aggregate data across groups. R1 can send R2 an XOR that combines data in groups A and B, and recovery happens much, much faster. Now this works in this simple case. What if you have hundreds of overlapping multicast groups? Are there any questions at this point, or? Okay, what if you have hundreds of overlapping multicast groups in arbitrary patterns? Well, here's how we handle it. A receiver belongs to multiple groups. Say in this case N1 belongs to three groups A, B and C, and it essentially decomposes these groups into regions of disjoint overlap. So N1 is in three groups and it breaks these groups into these regions. Now this is scalable. It looks unscalable, but it's not. And the reason is A, nodes are not interested in groups that they're not part of. So if you ran a traditional group-based protocol, it has exactly the same overhead. And B, the group membership service, whether it's gossip-based or it's centralized, is just a standard vanilla GMS that you're using for anything else. All this disjoint region decomposition is occurring at the end host. And another point to be made is it looks like there are an exponential number of regions, but this is bounded by the number of nodes that N1 shares a group with. So in reality, you won't have an exponential number of regions. Now what do we do with this? N1 does all this magic. It breaks groups into regions. Now remember that the basic operation in receiver-based FEC, the single group protocol I showed you, was that each receiver generates an XOR from incoming data packets. It selects C random guys from the group and it sends the XOR to them. In this case, it's picking 5 guys from the group and it's sending the XOR to them. Now we want to compose the XOR we send to a receiver based on the groups we share with it. If I'm in 3 different groups with another receiver, I want to aggregate data across those 3 groups. Hence, if I know what the regions of disjoint overlap are, now I know that, if I'm sending an XOR to a node in region ABC, I have to aggregate data from A, B and C. I know that if I'm sending it to a node only in A, it's not interested in groups B and C. I have to combine data only from group A. And so we just pick targets for the XORs not from groups but from regions. This allows us to selectively compose each XOR at the fastest rate possible. Now this means that we get scalability in the number of groups because we are running within each intersection, we are running the FEC protocol as fast as we can. So the definition of a channel here is now an intersection of multiple groups that you share with some other node. How does this work? Yeah.
I didn't understand that last slide.
Okay. So the basic operation of receiver-based FEC is I get a bunch of data in a group, in a single group. I create an XOR from it and I pick other guys from the group. So if we are in one big group, I just pick 5 of you and send you an XOR for data in group A. Now the point is that if you and I are in 5 different groups together, I could have sent you an XOR with data from all the groups. So to enable that, I first have to know whether I share groups with you. So in this case, let's say you're in an intersection AB, which means you are interested in data from group A and group B, but not in group C. Now instead of picking 5 random guys from the group, I'm going to pick random people from these intersections. So I'm going to pick you, the proportional fraction of 5 based on the size of the region compared to the size of the group. It's kind of regional sampling. I'm dividing this room into smaller chunks and I'm picking smaller fractions of the sample set from the group. It's like sampling within regions instead of groups. So it's like...
What divides into regions again?
Oh, the group membership? The group membership, exactly. The commonality in the groups I share with you. Yeah. Go on.
With the what are the black dots and the green dots?
The green dots are the nodes I happen to select, so the 5 of them. The black dots are the nodes that didn't get selected. So I want this kind of behavior where I'm just picking 5 green dots from the group A, but I want to do it on a per region basis. So instead of picking 5 guys from A, I'm picking 1 guy from AB and 1 guy from, and it all adds up to 5. Yeah.
Are the green dots nodes or packets?
They're nodes. Oh, they're nodes. Yeah.
Do you do the selection every time? When you
It's a little complicated. In the first version of the protocol, I create an XOR and then I select. In this version, I select and then I create the XOR based on who I selected.
How often do you really select those green nodes?
At the granularity of a single XOR. So if I know that I'm creating 25% of my traffic as XORs, there's a certain number of XORs I'm creating, and based on that, for each XOR, I end up selecting a node. Yeah.
Dynamic membership of multicast affect your performance?
It would, except in data centers, you don't have that much churn. That's kind of an assumption. That's why you can't use something like this in. It would still work because it's gossip based in some sense. So if you had churn, there'd be some kind of lag. But it would still work, but not as well, sure. Yeah.
Why do you pick one? Why do you only do one packet, like create one XOR and then send it 5 times?
That's what we do in the initial case.
Okay.
We can't do it here because different nodes need different XORs.
Oh, you select targets for the XORs, but you don't
Exactly.
send
The
same
nature of the
XORs.
XOR depends on the target because we want to compose the XORs faster based on the target. If I'm in 10 different groups with you, I want to create an XOR from those 10 groups.
Okay, then why are you selecting all the targets kind of as part of a single as part of a single step, right? Why not? It sounds then that like it's iterative. Like
in practice, it ends up being. This is how I'm showing it, but in practice, we're treating each of the regions separately, and we are doing what you're saying. Yeah.
Okay, so it does decompose into. In each round, I select a new node who's my target.
Pretty much, yeah.
Okay.
Yeah.
Just random. Hopefully amounts to random selection.
Yeah, exactly. It amounts to random selection, except you're doing it from regions. Absolutely.
Okay.
So how does this work? Well, on the x-axis, we have the number of groups each node is in. There are 2 different graphs. The one on the left shows the percentage of packets we are successfully recovering with this mechanism. And on the right, we have the latency we're recovering them with. Now, the point of this graph is as you make the groups finer and finer, as you take your system and you decompose it into finer and finer groups, your performance is not affected. For every other multicast protocol out there, including the ones developed by Microsoft, in fact, which are essentially the industry standard, the latency shoots up as you have finer groups. To the extent we actually ran it, and we found that with 128 groups, it's 400 times slower. And this is there's one reason, I'll have a slide later where I talk about this, but it's one reason why multicast hasn't caught on in data centers is because the reliability mechanisms have been so incredibly broken. They were designed for the wide area, they don't work well in data centers. So this shows that we get scalability in the number of groups, so you can tolerate a lot of low data rate group. And this shows the recovery histogram. So at different loss rates, we're recovering most traffic in that initial segment using the error correction. Because we don't have TCP/IP running on top, this is the final one. So we need a negative acknowledgement layer to catch the fraction of packets that FEC can't recover. So the bump in the middle is just this extra reactive layer. Now what does this mean? This means you can say that I want 20% overhead in my system, and that will be all you get for most packets. And if the loss rate is extremely high, then you have slight reactive traffic. And we tried it with bursty losses, and we found that because we have so much diversity in the encoding, it's extremely resilient to bursty losses. We can lose a burst of 100 packets in a row, and we still recover most of them at the same latency average. So one of the questions I get when I present this work is that, hold on, nobody uses multicast in data centers. As of 2008, that's perfectly true. Nobody does. Microsoft, I'm pretty sure, doesn't, and I know the other companies don't. And there are 3 major reasons why. One is that the reliable multicast mechanisms used were incredibly bad. They brought down, between 2000 and 2003, at 2000, practically every company that had a data center, and these were mostly financial institutions, were using IP multicast. And then they had a spate of essentially brownouts and blackouts, and people started phasing multicast out. There's a long list of companies that just kicked IP multicast out of their data centers. One reason was because the reliability mechanisms were broken, and we fixed that. We think we fixed that. But there were other issues. One is that if you have 1,000 groups in your data center, your routers and your NICs are not able to handle it. They can handle maybe 100 groups. Beyond that, everyone gets all traffic, essentially. And the other problem is that multicast is intrinsically dangerous. If you're all in a group, I can join the group, I can start sending data at my highest rate and bring the entire system down. So there seems to be fundamental reasons why no one uses multicast. And the insight is that, look, you want logical multicast capability because everyone uses that within data centers, but you want the ability to control it. So you have a layer of indirection in the kernel where you convert logical IP multicast addresses into a set of unicast addresses, or maybe one unicast address and a couple of IP multicast addresses and so on. So you know that your system, your routing system can handle say 100 IP multicast addresses. You use them for the high rate traffic. And that's something we're working on right now. So, yeah.
I didn't understand that slide.
Okay. We are talking about.
I got the first part.
Yeah.
So I didn't understand the solution.
So
how it is that now multicast will be not such a dangerous thing to use.
So here's what I'm going to do. The application still sees an IP multicast group. It joins, it uses a set sock opt, it does all that stuff. We're going to intercept that and we're going to convert it into unicast in the kernel. Now if you do that, you automatically get one thing: your routers are not unscalable anymore, right? You're just using unicast. The network is not seeing any IP multicast.
Okay.
Now the next thing we can do is, well, we can have IP multicast in the network, we just can't have thousands of groups, we can have maybe 100. So if there are groups in the system that have a lot of traffic, logical groups, we use the scarce IP multicast addresses for those groups, and everyone else is using unicast. So that's one step, and that kind of solves the routing problem, the scalability problem to some extent. Now if you have a kernel layer that's doing this, you can also have things like intelligent admission control. You can mandate who gets to send to what multicast group. So I can't just join a secure group and start spamming it. You have the opportunity now to add a security layer.
I find this very plausible, but it feels like now that you're giving up the efficiency benefits of doing multicast in the network layer, which makes me think, why would you stop here rather than moving further towards application layer multicast?
I think in a data center, the main sources of latency and overhead are at the end host. For example, I don't think overlays are a very good idea, because for most applications, if you have multiple hops within the data center, you're already in trouble. You go into the stack, you come out of the stack, massive latency. The other point would be that I think a major source of the overhead here is, why do you need IP multicast? Why can't you just do multiple sends? Because every time you do a send, you're going into the kernel. So if you can get rid of that, that's already a huge step in the right direction. So it's not really network efficiency, it would be end host efficiency that we're looking at. Yeah.
Just to make sure I understand, you're saying for the set of multicast groups that are not mapped to physical multicast addresses, there's some sort of kernel layer sub-bus or something where you are doing multiple sends? I mean, you have to be doing multiple sends somehow.
Exactly. The kernel is doing multiple unicast sends. Yes.
So maybe to put a finer point on John's question, as long as you've already addressed all the efficiency problems of now we're not taking a packet all the way up to user space and sending it 100 times, you've got this nice kernel level from sub-bus. Why not use that for all the multicast traffic?
You mean eliminate IP multicast entirely?
Right. In other words, if I'm understanding your question correctly, if you already have this mechanism in place for doing essentially non-network multicast.
We could do that. I don't know. I haven't built the system yet. I have a feeling that at the end of the day, if you have extremely popular groups, there would be value in having an IP multicast mechanism that's even faster than the kernel multisend. But I don't have a feel for the numbers. I can't. But you have a point. Maybe it would be pointless going.
Maybe my question is, you've done such a great job. Why aren't you using it for everything?
Well, I'll build it and then I'll measure it and then I'll know.
The key question is where's the break-even point, where the crossover point between where you get the efficiency from actual multicast being so much greater that it's worth using the real physical resource of the IP multicast group.
Exactly.
That break point you should be able to see in your data.
Yeah, exactly. That's pretty much the. So that's the technical part of this talk. I worked on a number of things. Most of them have this feel to it that they tackle a particular failure mode, they solve the problem. And frankly, at the end of the day, it's a lot of duct tape for data centers. Find performance problems where people are using retrofitted protocols within data centers and just fix it. But really, we've had 10 years of experience with data centers or more. Can't we come up with new abstractions? That sounds like a courageous thing to say, because distributed systems have this long history of failed abstractions. Do we really want to come up with more? But I think there's something fundamental here. We are not building the bridge before people want to cross over. In some sense, we're seeing all the people swim across and we're figuring out that we need a bridge. we need new abstractions. To some extent, the community has caught on and they are building new abstractions. Some of it is happening at Microsoft with Dryad, but people are dealing with a very specific data center application. How do you do data mining or database style functionality over very large data sets? Can't we go one step further? And here's what I think it should look like. This is something I saw in a paper by Jim Gray first, and it had a number of co-authors from Microsoft. And the idea was that there is a canonical system building paradigm for data centers. You partition a service across multiple nodes and you get scalability, and you replicate it and you get fault tolerance and availability. Now this is a very simple picture, and all the people I've talked to, every service I've seen running within a data center is built exactly this way. And each time they rebuild it from scratch. They take multiple operating systems running on individual nodes, they write load balancing layers, they start doing they build intelligent partitioning functionality into the load balancing layers. So why can't we build an operating system that just takes care of this? Now the phrase the data center is the computer, I thought I came up with it, but I saw it in an article by David Patterson like 3 months back in the Communications of the ACM, and he's a computer architect. So he says, can we come up with a new instruction set for data centers? What would an add be? Well, I don't think we need to go that far, but can we look at things like what a process is, what a process is, what a thread is, what protection boundaries are, what does a socket look like, what's an invocation to a service now that your service is spread out across dozens of machines. So can we come up with new abstractions? And that essentially is my goal over the next few years. I believe that now we have enough experience with data centers as a community to actually look at these problems and come up with new abstractions, and that they will be used. And if we do that, there are all these things we can do then. You have concerns like power and privacy. For example, if the data center OS knew what a partition was, it could mandate that data does not flow across partitions. And then you could trust third-party developers to write software that automatically manages privacy. And that's just one example, but I think you build abstractions, you can then hide a lot of complexity behind those abstractions. So to conclude, I presented a picture of a real-time data center that has to recover from disruptive events within seconds, and I talked about things you can do at the network level to enable this. Specifically, network level protocols that recover from lost packets in milliseconds. I think this is the tip of the iceberg. I think there's a long distance to go before we get anywhere near this goal. Thank you. So Ricochet is up for download. We rewrote it in C, there are 2 versions, and we are porting it into the Red Hat stack, in fact. Red Hat is building something called Cupid. It's a clustering platform that they're building right now, and we're trying to get them to use Ricochet as the clustering layer. And for that, we needed to do a complete rewrite. I'd be happy to, it's up on SourceForge actually.
I'm more interested in Ricochet myself.
Sorry?
I'm more interested in Maelstrom.
I didn't get
Maelstrom.
Maelstrom.
Maelstrom
That's what I'm more interested in. Ricochet,
I see, sure.
Not so much.
Maelstrom is, can you download it? Yes, it's a kernel module. I don't know if there's a link right now publicly, but if you send me an email, I'd be happy to send you the source.
Make us believe that your test bed actually is something that we should, the results that you're getting out of it.
You should believe it. That's a question I get a lot, which is why right now, at least for the wide area work, we are doing our best to actually set up a real optical network testbed. It's a lot of work because these are fairly expensive resources and they don't want computer science researchers near them. They're owned typically by the scientific community. But we are very close. If you see a journal version of this paper, that's exactly what it will add to this whole thing. Actual validation on an optical testbed.
So what is your testbed now?
The testbed is a combination of things. We set up a delaying layer on local clusters. So we have a bunch of, we essentially just put a lot of delay between 2 things. We were able to do that because the interconnect was big enough, but that's why we're limited by things like 1 Gbps. We can't run at 10 gigs because we just can't buffer and delay the packets long enough. The other testbed we tried was also MLab, which is again the same kind of story. It has enough capacity for us to do it, but to a point. What we're doing right now, and we already have that running to a degree, we are actually setting up some kind of a clever routing trick. So we'll send packet out into TeraGrid, but it's not going to hurt anyone, it'll just boomerang onto us. That may not be as real as we want, but it's one step in the right direction. But there's a huge problem here. I think in academia, we just don't have the resources to study these kind of networks. And it's hard to just muzzle into a working optical network because it's an extremely expensive resource. And arguably, the physicists and the chemists are doing real work on it. So, as opposed to computer science research. That's what they would say.
You can make the future physicists and chemists go 10 times faster with a network.
Right, you have to incentivize them, absolutely. The problem there is then you get stuck working on a very specific thing that they want you to do. I guess it's just a trade-off.